The masses of atoms are typically expressed using a unit called the unified mass unit, and the symbol U is used for this unit. So one unified mass unit is equal to 1.661 times 10 to the minus 27 kilograms. Now the mass of a proton and the mass of a neutron are approximately equal to one unified mass unit, although we'll be seeing that they are actually both just a hair over that. Now, when you're doing problems involving atomic masses and nuclear masses, you'll want to look at Appendix D in your textbook for the isotope masses. And you'll notice that they're given out to a very large number of significant digits. Make sure you use all of those significant digits, because for the problems that we will do involving atomic masses or isotope masses, having out all of those digits is going to be important. Now we can get yet another unit of mass for atoms and nuclei using Einstein's famous equation that the rest energy is equal to the mass times c squared. If we rearrange this equation and solve for mass, we can see that mass is equal to energy over c squared. So that means that another unit that we can use for mass involves an energy over c squared. So another common mass unit that we'll be using is MeVs over c squareds. So one atomic mass unit is equivalent to 931.494 MeVs over c squared. So this is a unit of mass. Another question that we can ask that's really important is, how big is a nucleus? We know that they're much smaller than an atom as a whole, but how small are they? The first person who had a good answer for this question was Rutherford. He shot alpha particles, and alpha particles are just helium nuclei, 2 protons, 2 neutrons. And he shot these alpha particles at other atoms, larger atoms, and the alpha particles started with a high kinetic energy. They were moving at a very fast rate of speed, and as they approached the heavy nuclei, they are positively charged because the 2 protons, and the heavy nuclei are positively charged, so they would repel each other, and they would stop. So the alpha particles would stop when the kinetic energy that they had when they were far away had all turned into electric potential energy. So if we conserve energy, we can see how close they were able to get. And so if we say the initial energy is equal to the final energy, so the initial kinetic plus potential energy is equal to the final kinetic and potential energy, these nuclei, the alpha particles, started out with a very high amount of kinetic energy. And they were very, very far away from the heavy nuclei, so there was no electric potential energy. So all of the energy was kinetic energy. Then when they got to the point where they stopped and turned around, at that point they had no kinetic energy, and all of the energy was electric potential energy, which is equal to K times Q1, Q2 over R. So we can say that the mass was the mass of the alpha particle, and we can put in what the 2 charges were. So the alpha particle has a charge of 2 fundamental units of charge because it has 2 protons, and the heavy nucleus, which was often something like gold, had the number of protons that it had, which we represent with Z, and then the closest, or the distance of closest approach, is D. So we can solve this expression then for D, the distance of closest approach. And we know that the size of the gold nucleus has to be smaller than this distance of closest approach. So by using this technique, Rutherford was able to set an upper bound on what the size of the gold nucleus could be. Now for gold, it turns out that you can get an experimental value, or he was able to get an experimental value of 3.2 times 10 to the minus 14 meters, which means that the nucleus must actually be smaller than this number. And this is kind of a surprising result if you think about the size of an atom. Electrons tend to orbit at distances of 1 times 10 to the minus 10 meters, so quite a few orders of magnitude greater than 10 to the minus 14 meters. So the nucleus was even smaller than this very small value. So typically when we talk about nuclear sizes, we express the size of a nucleus in terms of femtometers or fermis. And 1 femtometer or fermi is equal to 10 to the minus 15 meters. Now, nuclei are approximately spherical. You have all of these protons and neutrons jammed together as closely as they can get, and we can come up with a very rough rule of thumb expression that tells us the general size of a nucleus. So, very roughly, a nucleus's radius is equal to this constant value, 1.2 times 10 to the minus 15 meters, times the number of protons plus the number of neutrons, so this is the mass number, raised to the 1/3 power. And this will give us a very rough rule of thumb for the size of the radius of a given nucleus. So next, let's consider this first example problem. So we want to think about a copper nucleus and find the approximate values for its radius, volume, and density. So let's start out by looking at its radius. So we know that we have this rough expression that will give us a ballpark, at least, answer for the radius of this nucleus. So we have that R is equal to R0 times the mass number raised to the 1/3 power. Now in this case, let's see, well, R0 is always equal to 1.2 times 10 to the minus 15 meters. And in this particular case, we know that we have 65 protons plus neutrons in this copper nucleus. So that gets raised to the 1/3 power. So if we put that into a calculator, we get a value for the radius of this nucleus of approximately 4.82 times 10 to the minus 15 meters. So that would be our answer to finding the radius of this nucleus. So then we also need to find the volume. And the volume of this nucleus, well, if we imagine that this nucleus is roughly spherical, then we need to find the volume of the sphere with this radius. So the volume of a sphere is given by 4/3 pi r cubed. So if we put in the number that we get for the radius, that would be 4/3 pi times 4.82 times 10 to the minus 15 meters, and then that value gets cubed. So we end up with a volume of 4.70 times 10 to the minus 43 cubic meters. So really, really tiny. Then finally, we want to find the density. So in order to find the density, since density is mass divided by volume, we need to first figure out the mass of this nucleus. So since we're doing things just roughly, since we just found a rough value for the radius, we can get away with finding just a very rough value for the mass. So we can estimate the mass as being equal to 65 atomic mass units, since there are 65 particles, and we know that each proton and each neutron is approximately 1 atomic mass unit. So that means we have 65 atomic mass units for the mass of this nucleus. Now, if we want to convert things into kilograms, we can use the conversion fact that 1 atomic mass unit is going to be 1.661 times 10 to the minus 27 kilograms. And so the mass of this nucleus will approximately be equal to 1.08 times 10 to the minus 25 kilograms. Although if we wanted a more exact answer than this rough one, we could always go look up this nucleus in the appendix of the textbook. But it should give us a rough value for the mass. And so then we are ready to find the density. So we take that mass, 1.08 times 10 to the minus 25 kilograms, and divide by the volume, 4.70 times 10 to the minus 43 cubic meters. So then that gives us a result of 2.3 times 10 to the 17 kilograms per cubic meter for the density.